equivalent voltage, equivalent resistance, without looking inside the box? Can you make measurements just at the terminals to figure out what those quantities are? And the answer is yes. The first thing we do is define what we call the open circuit voltage. And that means we set this current to 0 and we look at the voltage we get. Well, if you look at this equivalent circuit, if you set that current to 0, that means there's no voltage drop across that resistor. So V is just equal to VEQ. So if you do that for a real circuit, you just open circuit the terminals, don't attach anything, you just measure the voltage. That voltage that you measure is the equivalent, the Thevenin equivalent voltage. Similarly, you can short circuit the current. So what that means is that you short circuit these terminals, you put a short across there. That sets the voltage to 0, of course, and then you measure the current. And when you do that, if you look at this equivalent circuit, that short circuit current is just going to be minus VEQ over REQ, and that's the negative of the Meyer-Norton equivalent current source. So by making measurements at the terminals, the open circuit voltage and the short circuit current, you don't have to look inside the box, as it were, to figure out what the equivalent circuits are. So let's go on to a simple example. And so to show these ideas, I want to find the equivalent circuits for this example circuit, and I could find explicitly the Thevenin equivalent. I could find the Meyer-Norton equivalent. Well, I'm just going to find the equivalent quantities VEQ, REQ, and IEQ. So the first thing we can do is set all the sources to 0. If you set the source to 0 in the Thevenin equivalent as a short circuit, and what you see from the terminals is just that resistor. If you set the current source to 0, that's the same as opening it up. And then again, you also see REQ. So here, if you look inside the box, we see we have a current source. A zero-valued current source is the same as an open circuit. No current flows for any voltage. That's the definition of an open circuit. And what I see when I look this way into there, I see R3 is in parallel with this series combination. So we can use our series and parallel formulas, and we get that for REQ. So that's the source resistance of our circuit. Now, suppose we want to find VEQ. I'm just going to use our terminal-only results. I'm going to open circuit the voltage. So there's nothing across here. This is 0. And now we measure the voltage. Well, this voltage is going to be given by some dependence on this current source. And since it's a current source, it's a whole lot easier to find the current through here. And then I'll multiply that by R3 to get the voltage. Well, because we have this in parallel with this now, from the point of view of the current source, I'm going to use current divider, which is going to be the other resistor divided by the sum of that one plus this series combination. And when you all get said and done, that's what you get. So here's the current divider part, and then I just multiply by R3 to get our voltage. So that is the Thevenin equivalent voltage for this circuit. It's a little more complicated than you might think, but it's pretty easy to find. And then finally, I'm going to find IEQ, which I'm going to do by finding the short circuit current. And I just put a wire across here, and so what that does, by setting this voltage to 0, that shorts out this, so that resistor isn't there. Doesn't matter if it's there or not. And so, again, I'm going to use current divider because I have a current source here. Well, the current I is going to be the negative of that current. And I use current divider, so current divider says that current is R1 divided by the sum of the resistances times IN. And I stick a minus sign in front because of the directionality of the current. And I get this for ISC, the short circuit current, which I know is the negative of IEQ. So we could have divided the equivalent voltage by the equivalent current to find REQ. In finding REQ up here, what we did was look inside the box. And you don't really have to do that, but it's nice to know you have a way of checking your answers. Set the sources to 0 to find REQ, find the open circuit voltage to find the Thevenin equivalent voltage, find the short circuit current to find the Meyer-Norton equivalent current source, and then the ratios should work out to be the other. Everything should check. Okay, so what do we discover? What we discovered is that all circuits consisting of sources and resistors are equivalent to one source, be it a voltage source or a current source that's in series or in parallel with a single resistor. No matter how complicated that circuit is, from the point of view of the connection points, the terminals, it is a very, very simple circuit. So that means that we can use either of these equivalent circuits, the Thevenin or Meyer-Norton form, the voltage source or the current source form, whichever seems to be appropriate, that makes solving the problem easy. What I mean by that is you're now going to attach something to the terminals and just determine things. And depending on what you're interested in finding and how complicated the circuit is you attach, you would use one or the other. Now, remember how we got started on this. Remember we were attaching our sink to our original circuit that we've been talking about. And the issue was what's called loading. And loading is a term that means that if I attach the wrong kind of load resistor for the given application, this V out will change. That's called loading down the original circuit. Well, I want to figure out what values of RL will not contribute to loading. What kind of resistor values can the sink have so that the V out doesn't change from what it is if nothing was attached? Well, we now know that our system looks like this, which is, I'm going to use the Thevenin equivalent because I have voltage that's the output, and the voltage I want is across RL. Well, what is V out for this really simple circuit? Well, it's the voltage divider. It's very easy to find. And what values of RL will allow V out to be equal to VEQ? Because when RL is infinity, that's the same as attaching nothing, and that's where we started. So I know that the output that I want is VEQ. Well, I think it's pretty clear that what we want is RL to be big. But big relative to what? And the answer is it has to be big relative to REQ, which is R1 in parallel with R2. So as long as the load is big compared to whatever this parallel resistance turns out to be, then you can attach the sink to the circuit and it won't change V out. However, if RL is smaller than that quantity or comparable to it, that output's going to change. And that may not be what you want. It depends on the application. This little simple example points out the power of using equivalent circuits.